So I want to do today several things. We have like 3 hours. We're going to have a break in the middle. And I want to cover several topics in supervised learning, mostly kind of the classic work, working first with linear classifiers and then talking about how we introduce nonlinearities, kind of the machine learning of the 80s and the 90s. But I want to start with something that I think you probably have talked about, and this is the perceptron. The perceptron is kind of one of the simplest models of learning, one of the earliest models of learning, right? It was introduced in the late 60s by Rosenblatt, and it also has like a very fancy name, right? Large aspirations, perceptron. It's going to solve perception, right? And there was a huge excitement and enthusiasm how a very simple algorithm can do amazing things. So the model, the learning model, is actually very simple. It's just a linear model. And the idea is that you get input, a set of labeled samples. And each input is a vector in RD. And you have, let's say, n such vectors. And each one of them has a label. And the label is binary. It could be +1 or -1. So these +1, -1. And the model is actually very simple. You want to find some weights, and you want to predict the following. So the prediction of the model, the predicted label, is going to be the sign of W transpose X. So if someone's give you a new sample X, you multiply it, just dot product with W, and you look at the sign. And if it's positive, you say the label is +1. If it's negative, you say -1, right? You've passed that, right? You've done that. Great. And of course, what you want to do is you want to select a set of W's that agrees with your training data. So you want to find W such that, right, we are looking for a W such that the sign of W transpose Xi is equal to Yi for every sample, right? So you want to find a classifier, the weights, the parameters of the model that agree with your training data, with your label data, right? I just want to make sure that we have this, we speak the same language. I don't see enough nodding, so I'm going to say it again and again until you, OK, good. OK, kind of a car dog. So Rosenblatt introduced, and he was very excited to introduce this Perceptron algorithm. Do you remember the algorithm? Can you tell me what the algorithm is? OK, brave on the left. Yes.
I remember that he tried to predict if it's a square, a triangle, or
it could be, but this algorithm is actually quite general. And the idea is that the claim is, and that was actually proved by Rosenblatt, that it can learn to separate any linearly separable data. So if you have a set of labeled samples, Xi, Yi, which are linearly separable, then it's going to learn the right W's. The Perceptron algorithm is going to find the W's that indeed separates the data, the training data, right? You have no guarantees about the test data. Any hints about how the algorithm goes? OK. Let me remind you. So the idea is that you basically go over the samples, sample by sample. So the Perceptron, with a capital P. So this Perceptron algorithm says, initialize W to something, let's say 0, or something small, some kind of random small numbers. Usually you don't initialize exactly to 0 because then nothing moves, right? To something, let's say something small in RD, right? The vector W is also in RD because you have a dot product with X. And now, basically, you do the following. You repeat you repeat the following until everything works, until no new changes are needed. Let me just say that until you're done. I'm going to explain that in a second. And then what you do now is you go over the samples. Let's say from 1 to n. And for each sample, you basically check if it is already correctly classified. So you basically check if it is correctly classified. Then what you do? Nothing. And I mean, formally, what does it mean that it's correctly classified? Right, exactly. If this holds, then you do nothing. Otherwise, what you do, you change W, and what you do is you add to W yi times xi. And sometimes, and this is perhaps the way you learn it, is that you have a scalar here, kind of a step size. The original algorithm that actually has that as 1. Now, when I said repeat until done, I meant you repeat that until all the data is correctly classified and you need to do nothing. And there's a proof that this algorithm would stop. Now, this is not really trivial. Can you see why it stops? Yeah?
Because you're not going back to recheck if what you've correctly classified is still correct. So you're just changing it enough until everything is correct at least once.
That's true, but in a way, you see that you go over the data, and then suddenly you make a change to W. So it's really possible, in principle, that once now you're classifying well the sample 17, but you heard sample 5 and 12. So it's actually really hard to see just from the algorithm why is it that in general you keep improving. And it's not clear from this directly from the algorithm. And actually the convergence proof is not a constructive proof. It just shows you that it has to stop. It doesn't show you exactly why and how. That's the original proof. OK. Let me just, a side note. There's a way to rewrite this. And the idea, in a way that basically uses the fact that, oh, sorry, this is, no. What I meant is yi is the sign of, right? Yeah. W transpose x is a number, positive or negative. Yi is plus minus 1, right? So you need the sign there. So there's a way to rewrite this. The sign function is kind of an ugly function, right? Because why don't we like the sign function? It's not continuous. Yeah, it has this discontinuity exactly where you're interested in, right? Where it moves from negative to positive, it's incontinuous. So that's actually annoying. And so and we can rewrite this condition in a way that is easier to work with. And if you've done that before, just tell me, OK? So what does that mean? That means that, in a way, what is OK, I'm going to tell you how you rewrite this, and then we're going to see that it works the same. You can look at it as the following question. You can check if yi W transpose xi, you can check if it is larger than 0. And here's what happens. This is larger than 0. There are two cases, right? Either this is positive and that is positive, right? This is larger than 0. Either yi is larger than 0 and W transpose xi is larger than 0. So they have the same sign. Or, right, they're negative. They're both negative. And they also have the same sign, right? So instead of writing this condition, we can just write that condition. OK? Good. And of course, feel free to stop me if something is not clear. Even if everyone's nodding, I mean, we didn't get to the point where everyone's nodding. So if you have a question, probably other people also have that question. So raise your hand and ask. Yeah, good, great.
Y is 0.
Right. So our y has to be +1 -1. But you're right. What happens if W transpose X is 0, right? This is this weird case that you're exactly on the on the separating plane, and the probability that this will happen is negligible. So this does not happen in practice, and you can break the tie. You can just say, yeah, let's look at what happens if it's larger or equal to 0, or you can decide it's not, right? Doesn't really matter. Okay, so we can replace this guy with the following condition. Okay, so I want maybe I should spend another 2 or 3 minutes giving some intuition about this quantity. Maybe that's a good idea. I'm trying to feel how much you already know about this. Let's spend a few minutes on this, just that you feel it. Okay, let's say we have some data. Some samples. That's the first coordinate of x, the second coordinate of x, and you have some positive samples and you have some negative samples. And we're basically looking for a W that separates the pluses from the minuses, right? You want it such that all samples from one side of the hyperplane are positive and from the other side negative, right? If you have the right W, let me just remind you, all the points on this line, they actually obey a linear equation, which is exactly W transpose X equals 0, right? That's the definition of a line. And this means that as you go to one side, W transpose X grows, right? W transpose X becomes larger and larger than 0, right? It's become more and more positive here and less positive here, right? And so this side, W transpose X becomes more and more negative. So in a way, I want to give you this intuition that W transpose X, its magnitude tells you something about how likely it is to be positive versus negative, right? If you're here, it's really, really positive. It's probably, you should be really confident that you're in a positive class. And if you're there, it's really negative. What I'm trying to convey is that W transpose X, even if you only look at its sign, actually it has more information than just the sign. It's not only if it's positive or negative, but also the magnitude of how positive it is. Okay, and this could be, and we're going to see that it's also important. Questions so far? Yes.
Doesn't parameters an optimal split because parameters a split, correct?
That's right. That's right.
Theoretically, the line could be almost straight down, and then being more left doesn't necessarily mean you're more.
That's an excellent question, and this is exactly what we're going to do. We're going to look for one best separating hyperplane, and we're going to follow this intuition that you just raised. Yeah. Other questions? So back to the way you described it, what the Perceptron algorithm tries to do here, it just tries to find a line that correctly classifies the data so that the sign of W transpose X agrees with the sign of Yi, right? So I described to you this algorithm, but it's really not clear why it works. So let's forget about it for a second. Let's hide it. I really like these boards. And let's try to invent another algorithm just to solve that problem. You learned about gradient descent and stochastic gradient descent, right? Good. Yep.
Is
Will the algorithm converge if the samples aren't 100% separable?
No, it would never stop. Because the stopping condition, which is included, the stopping condition is you only stop when everything is correctly classified. So if the data is not well separated, like this, that algorithm would not stop. And this is a big problem with the algorithm, right? Yeah. So let's invent a simple algorithm to solve, to find the best, a linear classifier that separates the data. So one idea that people follow is to say, okay, let's define a loss, a penalty that we need to suffer for every W. So for every W, I can compute how bad it is. It's kind of a pessimistic view, right? You always pay penalties, but so how would you do that? What kind of loss would you like to use for this problem? Suggestions? Yeah.
Cross entropy.
Cross entropy. Cross entropy is a measure between distributions. And here, I actually did not define a distribution. Yep. Mean squared error between what and what?
What I would expect the labels to be and what the labels actually are.
OK. Yeah. So the suggestion is suggested loss. You're saying, let's look at yi minus w transpose xi squared. And you can sum that over all samples, right? Yeah, or average, or yeah. Yeah, that's a good idea. We can do that. That's a good idea. I mean, that was the suggestion, right? Or the sign of. No. Just this. Yeah. I think it's a good suggestion. You could also, what happens if you use the sign? I mean, the benefit of this, that this is differentiable. You can derive it and run it. Yeah, I think it could work. If you add the sign, then you have this problem. Let's look at the alternative. What happens if we add the sign? The problem here is that the sine function, I remind you that it's a horrible function, right? Because it looks like this, right? And this is really bad for, let's say, gradient descent. Why is it bad? Because it's not differentiable here, right? At 0, it's not differentiable. And also, everywhere else, the gradient is 0. So if you want to do gradient descent with this function, it's either not defined or you're doing nothing, right? So this is like the worst function for a sine function. This would be a problem if you use that. So this is also the problem why you don't want to use the following loss. Here's another loss that you don't want to use. You could have what is called like a 0-1 loss. This was like L2 loss. 0-1 loss could be, you just count if yi equals to the sign of w transpose xi, right? This is kind of an indicator function over this. It's 0 if they are equal. If you pay a penalty if they are different. So this is again a problem. You don't. Now I want to show you. Let me just visually show how this loss would look, because I want to use this loss to devise a better loss. But let's just plot how this would look. The x-axis now that I'm showing to you is the following. I'm showing you yi w transpose xi. This is 0. So let's see what the loss is going to be as a function of yiw transpose xi. I know that usually you're used to something else on this axis, but we already talked about this quantity. What is this quantity? It's how far you are from the separating hyperplane. But you also multiply that by yi, because if you're negative, you multiply it by a -1, and if you're positive, you multiply it by +1. So it's kind of fold the two sides of the plane to the same direction. So if this is large, then you correctly classify, right? We've seen that if this is larger than 0, you classify correctly. So this loss basically looks like this. You pay price of 1, right? Price of 1 if this is negative, and you pay nothing if this is positive. So this is the 0-1 loss. OK. So as with the sine function, this loss is actually, it's not differentiable. You're not going to gain anything by doing gradient descent using it. So people suggested to relax that a bit. And instead of paying a penalty, a fixed penalty every time you're right, fixed penalty every time you're wrong, how about you pay a penalty depending on how wrong you are? So here's another loss. And that's your loss. So here's what this does is, if you correctly classify, if this is larger than 0, you pay nothing. If you're wrong, you pay depending on how wrong you are. And linearly, how far you are from the wrong side of the line, that's how much you're going to pay. OK? And this loss is called, you've seen this before? Oh, so some people said ReLU. And this always happens because it has the same shape. But the axes are different. So this is why graphs are confusing. It's really important what's written on the graph. This is how much you pay as a function of these yiw transpose xi. ReLU is something else. ReLU is what's your output given your input. And they both look very similar. Yeah, someone said it's going to look like this, but the important part is that these functions look the same, but the input and output are different. So have you seen this function before? This loss function? OK, good. So it's called the Hinge loss. And it's called Hinge. Hinge is a tzir banglit, like a door hinge. So it's called Hinge because, I don't know, it's a silly name, but that's what it's called. OK? So the advantage of this Hinge loss is now that you can, I can do that. The advantage of the Hinge loss is I promised him that I'm going to dance, but good. Now you can see what happens if you try to run a gradient-based algorithm on this. Let's say stochastic gradient descent. So let's write a stochastic gradient descent algorithm using this loss. So the loss again is going to be so the full loss is going to be something as if you go over all samples, right, of, let's say, Hinge loss of yi, xi, and w. But when you do stochastic gradient descent, you learn stochastic gradient descent, right? You sample, let's say you do 1 by 1, not batches. You sample one sample, draw randomly one sample, and then you do a gradient step for that sample, right? So let's compute, if this is the loss, let's compute the gradient. But first, let's write this loss formally. Let's write this loss more formally. So this loss, if yi double transpose xi is larger than 0, then the loss is 0. What happened otherwise? Exactly. So it's just minus y double transpose xi, right? This is like the just the identity line, right? Y equals minus x. Yep.
Just one question. So this loss doesn't like say how confident are you right? Let's say you are 0.50001.
Yeah.
You have no loss.
You're lucky. You faked it. You almost did, but you gambled. You guessed correctly. It's as if you knew what you were doing. It's like an exam, right? You fill an exam, you guess correctly, no one questions you. But if you're wrong, someone looks, oh, why did you do? Maybe it's a silly mistake. So that's a loss. And you're right, it's asymmetric. We only care about the magnitude of a mistake, not the magnitude of correct guesses. So what would be the gradient of this loss? Do we have a better? So I'm looking at the, oh, sorry, we need to do the gradient, right? The gradient of the loss. And it again has two components. What happens if yi double transpose xi is larger than 0? The gradient is 0. And what if otherwise? So this is the gradient with respect to w. So you have minus yi xi. Right? Yeah, that's easy. So let's write the stochastic gradient descent algorithm. I'm going to write it here. So how does the stochastic SGD works? Let me just write SGD with Hinge loss. So how does that work? You sample, right? Sample a pair xi, yi. And then you take a step, a gradient step. Gradient step means you take a step in the opposite direction of the gradient. So, so let's see, a gradient step. So basically we have if yi w transpose xi larger than 0, then we take this gradient step, which means do nothing, right? And otherwise, we need to take a gradient step that is minus that, right? So the gradient step is going to be w minus the minus yi xi. So this is basically plus xi. And sometimes in stochastic gradient descent, you have a step size. And you set the step size. There's a parameter here that could be the step size. Did you, by the way, did you talk about how to select the step size?
We covered it really shortly,
OK.
but we kind of discussed about the pros and cons of having a large step size, a short one, doing something which adapts over time, gets smaller by the error.
Excellent. So let me just mention shortly that there is theory that can guarantee convergence of gradient descent, not stochastic gradient descent, gradient descent, if you select a step size that is not too large and not too small. And this depends on the derivatives of the function that you try to optimize, right? So it should be somewhere between the steep 1 over the steepest derivative and the most shallow derivative. And by the way, with this loss, the derivatives are at most 1, so selecting a step size of 1 should actually be okay. So when you do stochastic gradient descent, we sample one sample, and then you do this update. Then what? You repeat that, and you repeat until what? So now actually with SGD, maybe it's never going to stop changing, right? Because maybe the function, maybe we can never reach zero error. But you're right. If the data is linearly separable, and let's assume this algorithm can find it, then it would reach the case where everything is correctly classified. But you could stop even if it's not, right? Then what are other conditions that you usually stop? Just
You can choose a very small number.
sorry?
Choose a very small number or a number that
Right. When you reach an error that is good enough for you, you don't care. It's 1%. That's okay. Or yeah, if just it's running for a long, long time and you just got impatient and you want to stop, right? That's also a criteria. Yes.
error doesn't change.
If the error doesn't change, right? It reaches a plateau, and you think, okay, that's going to stay there. So here there are several conditions that you can decide to stop. So there are like various conditions. Okay. Now I'm sure you have noticed that this algorithm actually resembles the Perceptron algorithm. And this is, I think this is a really nice result, because when the Perceptron algorithm was introduced, it was not defined in terms of stochastic gradient descent. But if you just look at stochastic gradient descent with a hinge loss, suddenly you have an insight. Now you can understand why this algorithm kind of converges, right? Because you understand that you take steps, right, that go down to the minimum of you take gradient step, stochastic gradient step, looking for the minimum of the loss function. There are several differences, right? Can you spot them?
What did you say? What's the difference between what?
Yeah. What's the difference between the original Perceptron algorithm and the HGD with the hinge loss? Yep.
This is stochastic. Meaning it only works on one sample at a time. We don't work on all samples.
Yeah. So that's right. So the way we sample is different. What happens here is you basically go over the samples in a fixed order, 1, 2, 3, and then one. You go through the samples in the same order every time, and here you just sample them differently every time. By the way, what people often report is that what works best is to take your data. If your data is small enough, you take your data, you create a random permutation of that, and you go over all the data. It's like you do today. You have like an epoch where you go over all the data in random order, and then in the next epoch you again go over all your data in random order. And this is actually different than this. But it's also different than this because here you take the same order every time. Right, so this is a major difference, the way you sample during optimization. Yep?
The loss. So here you don't have a different loss for positive or negative, right?
Well, the loss is actually, I mean, the condition is identical, right? You only make a change based on the sign of yiw transpose x psi, right? The same as here. This is actually the same. Okay. Yes?
This one could theoretically work if it's not linearly separable.
Excellent. Excellent. Because the stopping condition here is really harsh. You only stop, you're kind of a perfectionist, right? You only stop if everything is correctly classified. And then if the data is not linearly separable, then you're going to never stop, right? And there it's kind of a more lenient stopping condition, depending on how you define it. Yeah. Yep.
The YI XI there in the update row.
Yep.
How did we get to that again?
Here or there?
Here, in this one.
You know, actually, so there is a geometric intuition that I can explain. I don't know if this is why Rosenblatt devised the algorithm this way. But one intuition is the following. See what happens. Let's say you have a W, and you have this sample XI, and it's not correctly classified. So this product is negative. See what happens now. Now you added this thing. So let's see what happens at the next iteration where you encounter that specific sample at the next iteration. So now you have YI, but you have a new W, right? You have this guy. This is the new W, right? So you have what you had before, but now you also have this term. You have yi squared, and then the norm of xi squared. Now, this is positive, and this is positive. So this means that every time you do this update, that condition is more likely to be obeyed because you basically add a positive term. So for that specific sample, you keep increasing this side, and at some point, you're going to be positive. Does that make sense? Yeah. But of course, there could have been other ways. I think what happens inherently is that somehow at the back of someone's mind, I mean, the hinge loss is hiding there, right? It was not defined in this algorithm, but the fact that it matches this hinge loss is nice. OK, more questions? Before I switch to talk about SVMs, just a bit of history. I don't know if you talked about this. You know, perceptrons, there was a lot of excitement. The feeling was, look, this is a very simple algorithm, right? You write it, just a few lines of code, and it can actually learn from data and it generalizes, right? Because if now you have new samples here, yeah, it will correctly classify them. And that's impressive. Very simple algorithm, does learning from data. This is the end of the 60s. And Rosenblatt was very happy running around and describing this new invention. Then there's the question of how, is this an interesting problem? Is it really interesting to learn from data that is linearly separable? And one claim put forward by Marvin Minsky from MIT was that this is not the set of interesting problems. And actually, Minsky and Papert wrote a book called Perceptrons. And in this book, they put a very convincing arguments why all these perceptrons, this is not interesting, because real hard problems like perception or AI, they are not, inherently, they are nonlinear. And you don't want to do linearly separable data. And did you talk about this? No? So this is worth mentioning because it will be connected to your deep learning course. Minsky gave a very simple problem that is very easy to solve, but cannot be solved with perceptrons. And this is the parity problem. So the parity, yeah?
I have a question about the claim.
Yeah.
In physics, I mean, the world is non-linear, but we always make approximations of linear elasticity or just linear theory in general because it's easily solvable and it's just solvable in general. But can't you transform problems that are not linearly separable to be linearly separable in some other dimensions and make them perceptron worthy?
Yes, yes. actually, the answer is yes. This is a very fruitful direction. And you know what? Keep this question just a bit, and maybe we can follow what you're doing. And actually, we're gonna address that point in more depth later today. But let me describe the parity problem and remind me again this question. And let me say that actually Rosenblatt made exactly your point. His point was not that raw data must be linearly separable. But the idea was that you can take a data and maybe transform it in some way to some representation where it is linearly separable. And then you can run the perceptron. But now the problem was, OK, how do you do that? Where do you find these nonlinear transformations? So the challenge remains, how can you learn these nonlinear transformations together with the perceptron at the top? And in a way, this is what deep learning does. It learns this nonlinear transformation together with the perceptron at the top. So that's a very important question. There was another question? OK. So let me describe to you the parity problem. OK? Here's the problem. I'm giving you a series of bits, 0, 1, 1, 0, 0, 1. And basically, you should tell me if the number of ones is even or odd. OK? Can you devise an algorithm to solve this problem, children? Well, it's an easy, right? How much? What do you need? All you need is just one cell, right? Memory of 1 bit, right? And you start with this bit being 0. Every time you have 1, you increase it by 1. If you see another 1, you decrease it back. It's even, right? Every time you see 1 in the input, you just flip the bit back and forth. And at the end, so what's the memory complexity of this algorithm? 1 bit. You cannot do better, right? What's the runtime complexity of this algorithm? O of n. You just and the constant is 1. You just read the input, right? That's really the easiest algorithm. So the problem seems laughable, right? It's a very easy problem to solve with standard algorithms. The problem is that Minsky showed that you cannot solve this problem with perceptrons. And let me convince you in that. And actually, it's easier to see if you limit the sequence of bits to have only 2 bits. So really, this is the simplest problem ever, right? I'm giving you 2 bits, and I'm asking you, do you have an even number of ones? That's really easy, right? Let's see geometrically how this looks. So we're going to be the positive class if you have an odd number of ones. So if you have 0, 1, this is a plus. If you have 1, 0, this is a plus. But if you have 0, 0, minus 1, 1 is a minus, right? So this is an odd number of ones. This is an even number of 1. And convince yourselves that this is not linearly separable, right? Try to imagine a line that separates them, right? You cannot do that. So this is a strong example, right? Because it shows you a very easy problem that is not learnable with perceptrons. Because it's not linearly separable, right? So actually, these arguments, and in a way, I mean, this is a very simple problem, but in his book, Minsky discusses other problems like perception. And actually, it's very interesting. It's actually a very readable book. I actually recommend, if you have an hour, give it a read. It's very readable, actually. Surprisingly readable, not that much math. And at the end, there's a nice, the last chapter has kind of a Q&A, and where Minsky kind of asks questions, and responding. You know, it's easy to win when you both ask the questions and the answers. But one of the questions is something following your comment. What happens if you can do these alpha perceptrons, where you first learn a representation and then you learn a perceptron over that? And Minsky says, well, we don't know how to do the first stage, so this is not useful. We know today this is not true. You can't do that. But what happened was that this book of Minsky actually kind of killed machine learning, right? This learning from data approaches, it kind of killed it for a decade. Maybe also killed Rosenblatt. He was mysteriously killed in a boat accident. But yeah. OK. So this hour, we're going to switch to a class of linear classifiers. It's an approach called SVM. But just before that, I think I owe you a response about nonlinear transformations before we run a linear classifier. So I just want to give you like simple examples. And I understand that Hanan talked with you about the case where you have data, and then you look at like polynomial functions of your input. You take your features and you multiply them. So let's just give just a simple example of why it's useful to do kind of a nonlinear processing. So here's just a simple one, OK? Let's say we have a lot of minuses here, and we have a lot of pluses around. OK, something like that. What would be a good classifier? Well, this circle here, right? But it's clearly not linearly separable. Right? There's no way. But you can transform that with a very simple nonlinear transformation. If this is x1 and this is x2, you can just take, let's say, x1 squared plus x2 squared. This is, of course, the distance from the origin. And this would map you to something that looks like this, a lot of minuses, and then pluses, right? And you know, if this is around 1, then there's b, right? Now this becomes very simple to classify with a linear classifier, just that linear classifier, right? So sometimes linear transformations can help you. More generally, you can think about it in the following way. I like to think about it as, do you do, I don't know if you have kids and you do birthdays sometimes. So you have a balloon, you inflate a balloon and you paint this smiley face on the balloon. And then at some point after the party, all the air comes out and the balloon now looks very, I mean, the face doesn't look a face anymore. It looks very weird. Because in a way, the balloon went through a nonlinear transformation that distorts the space. So you can think about data, perhaps it's not linearly separable. But if you do this nonlinear distortion, you know, if this was drawn on a balloon and you kind of distort it, you can maybe distort it in a way that is linearly separable, right? So before you do the transformation, there is a separation, but it's not linear. And instead, what you can, right? So here, this is the original data with a nonlinear separator. You do a nonlinear transformation, and then you have a linear separator. OK, we're good. But you got the idea. OK, so that was just a comment I think I owed you. And we're going to talk about this more in the third hour. But what we want to do now is, there was a question earlier today about, well, this is one separating line. But there are others, right? So I usually do it this way. Oh, OK, there is this. Let's do it from scratch. So we have some pluses, and we have negative samples. And I'm asking you, where is the separating hyperplane? And you tell me it's there, right? And then I do this. Do you like this separating hyperplane? And you say, not very. What should I do? More like this, right? And then I do this. And do you like this hyperplane? No. Why don't you like it? Because you intuitively feel that it should be somewhere perhaps here, right? This is much better. Now, I mean, that's our intuition, right? So intuitively, you want it to separate the data. You don't want it to be right near the data points. Because you understand that intuitively, these data points, they might be noisy. Maybe they should move a bit. So if you put the separating hyperplane here, well, maybe there would be at test time, maybe there would be other points that are not exactly there. So we want kind of take a safety margin, right? If we can, we want to be as far as possible from the data. So that's very important. I mean, look, all these 3 lines that I pass here, they were all perfect on the training data. But you know that we don't care about the training data. We want to be good on the test data, right? And maybe that's important to understand. When people talk about the perceptron, the notion of generalization of how well you do on test data, this was not in the game, right? People only talked about how can you learn to classify the training data. But of course, we usually care a lot about the test data. Sometimes we also care about the training data. We always care about the test data. So now the intuition is, OK, let's try to find a separating hyperplane that not only classifies your training data, but would be good, would generalize well. Right? It's going to be good, performing well on the test data. And maybe one way to do that is to select that separating hyperplane that is far, that detects a large safety margin. Right? That's pretty intuitive, right? It's a good, sounds like a good goal. Good. So let's try to do that. So we need to formally define what's the safety margin. So let's write that. Let me just put this aside a bit so I have some more room. Just a side comment. Until now, whenever I describe to you linear classifiers, I always talked about W transpose X. But this limits you to lines or hyperplanes that go through the origin. In general, what you want to do is also to add some bias. So instead of having lines that all go through the origin, you also want to have lines that there's some bias, right? So you shift, right? Sorry? Yeah, and the writing this plus b is just annoying. It makes notation cumbersome. So usually you just think about it as if x is in a higher dimension. You just add 1 at the end of your x. You talked about this, right? Yeah. Great, good. And you know, I think in some packages, like I think in MATLAB, if any one of you is still using MATLAB, sometimes they do that automatically for you. If you run some regression problems, they just add the column of 1s without telling you. I mean, it's so common that it does that. So I'm still going to talk about W transpose X. All the development, all the derivation of the math should include the plus b, but I'm going to put it aside for simplicity of notation. OK. So what we can do, so let's say we have our we have our separating hyperplane, and we want it to be far as possible from the samples. Let's see what is this distance. Let's say that we have a sample xi. What is this distance? It's actually, it's yi w transpose xi, right? We talked about this. This is exactly the distance from the separating hyperplane. And of course, I don't want it to be sometimes negative and sometimes positive, so I just multiplied by yi. So if you're on the right side, it's always positive. So we basically want these to be large, but we can also define, the margin is defined as the closest point. We're not going to care about the distances to all the points. We just care about the closest points, the ones that are closest to the separating hyperplane. Now, usually you can imagine, usually there's more than one, right? Because if there's just one, then it could wiggle, right? But if there's two, you can kind of lay the separating hyperplane. You have like two things that hold it, that support it. This is why the technique I'm going to tell you about is called support vector machines, because you have these supports that support the separating hyperplane. It's kind of a silly name. But my point is that we want to look at those samples that are closest. So if we have, this is the margin of the I sample, we want to look at the margin of the closest sample. So we're going to define the margin to the minimum over all the samples of the sample margin. Yep.
Why? Because if it's not linearly separable,
we're going to assume it is linearly separable, and we're going to relax this assumption later.
Okay.
Right. But you're right. If there's a minus here, then we're in trouble. But let's assume that it's linearly separable. Yep.
But aren't you more vulnerable to outliers?
Sorry?
If you look only on the minimal distance, you're more vulnerable to outliers.
So there are two. No, actually, you're less vulnerable to outliers. Assuming that the data is, OK, so outliers could go both ways. You're less sensitive to things that are here, right? If something is here, so this approach says, you know what? I only care about things that are near the separating hyperplane. If something happened here, I don't care. This is clearly positive. By the way, this is not true, but this is clearly, I don't care about this. So this approach tells you I only care about what happens near this. And you're saying, what happens if there's some noise here and suddenly you have something here? You're going to be really sensitive to that. And you're right. This is somewhat related to the problem where the data is not linearly separable. And we're going to address that in half an hour.
On the right side of the line, then your support vector wouldn't be, like for that point, it's not very representative for what it is for vertical.
Right. If you have something, I mean, this is the same problem. If you're here, then you measure something, it's not the right margin. If you're here, you're going to move the separating plane here, and that's not going to be the right margin. And you're right. We're going to handle that together with the problem of maybe label noise or something that's nonlinear separable. But we're going to start with like the simple, let's assume the data is nice first, and then see what we can do, and then we're going to address exactly these points. This is an excellent point. Yes?
Could you say why you multiply by yi?
Oh, yeah. Because if you don't multiply by yi, this distance is going to be positive, but this distance is going to be negative. And I want and then it messes your computation, right? Basically multiplying by yi is a way to write in a short way something that otherwise you need an if. You can say, oh, if it's positive, then do that. If negative, do other.
Taking the absolute value of that.
It's not exactly, because it cares about the class. You write it as if everything is nicely separable, it does what you're saying. It's taking the absolute value. But later, if we're going to have outliers or nonlinear separable data, it's going to be different. OK. So this is the margin. It's the distance to the closest points, and usually there's more than one. OK? This is the margin. And what do we want to do with this margin? We want to maximize the margin, right? So basically what we want to do is we want to maximize the margin. Maximize over what? Over W, right? We want to find the W that maximizes the margin. I didn't bring my printed notes today. Just have this. Let me say. So just note, if you want to maximize this term over W, there's something very simple you can do. If you look at this term, how can you make this term large if you're allowed to play with W? Just grow W to be large. Let's say if you have a solution, multiply W by 2, and then by 2 again, right? You see that if you want to maximize this, just take, just make all the entries of W very large, and it just, goes to infinity. So actually, this is not a very good representation of the margin. What you want to do is probably, I think what we want to do is divide that by the norm of W. And now, if you have a W, if you have a separating hyperplane, by multiplying the entries of W by a scalar, it just keeps it in place, and it also doesn't change the margin. Let me talk about this again just for a second. Look at this. We have a W, and we have this separating hyperplane. What happens if you multiply the entries of W by 2? It's going to be a different W, but it's going to be the same hyperplane. It's like you zoom in or you zoom out, right? You change the scale of the problem. You kind of move from the last row to the first row. Everything looks larger, but it's the same separating hyperplane. So you want to define the margin in a way that does not depend on the scale of W. So what we want to do is define a margin in a way that does not depend on the norm of W. And you can see that with this definition, if you multiply all the entries of W by a scalar, let's say 2, the margin, this is going to be double by 2, this by double 2, and the margin is going to be the same. OK? So this is more like the correct geometric definition of a margin. OK, so now we have an optimization problem. Let me write it in full. We want to maximize over W the minimum over I of yi W transpose xi divided by the norm of W. That's great. We have an optimization problem. We're done. Except it's not really clear how to optimize this, right? You have maximum, you have minimum. This is not, and these functions are not differentiable everywhere. It's not exactly clear how to do that, how to optimize this efficiently. So here's what we're going to do. We're going to take this optimization problem, and we're just going to rewrite it in a way that's going to be easier to optimize. OK? But before we do that, any questions about this? Does that? Yep.
Why do we need the assumption that there are several points at the same distance from the vector?
We don't need it. We don't. I'm just telling you, in practice, it's going to happen, because intuitively, if your separating hyperplane is very close to the positive ones, you want to increase the margin. You're going to push it away, and at some point, it's going to reach the other side, right? So you expect to have same margin from the right as the margin from the left. It's going to look, you expect it to look something like this. There's going to be like these distances. This is going to be the margin, and there's a separating hyperplane, and there are like safety zones on both sides. And they're going to be the same size, otherwise you increase it. Yeah. Yes?
I got confused with the maximize and the minimize.
Yeah.
Again,
Yeah.
time, so.
That's confusing a bit. The point is that we define the margin per sample. This is rho I. And rho I is just the distance of the ith sample. And then the margin that we care about is the margin to the closest samples. The ones that are closest, right? Minimum over I, over all the samples. And this is what we want to maximize. So we want to maximize the margin. So maximization is over the parameter of the model. This is what we want to solve. But we have this minimum because it's kind of a worst. Yeah, we want to increase the worst margin.
But that is like if we, it's a silly question.
All questions are silly.
That is if we have to take into account both sides, yeah, because otherwise, if you maximize W for the minimum, you maximize it for everything anyway.
Right. I mean, you could define other problems. Here, we maximize the margin just of these, and we don't care about the others. Look, if these samples moves here, that's not going to, that's not going to affect your solution. So in a way, this SVM problem, it is only sensitive to the samples that are near the separating hyperplane. You could have decided, well, I'm going to average across all margins, not just the closest ones. You could have done that, but you don't.
What I'm saying is that, let's say that, you have to do it, it's a constraint problem. You have to do it for both sides at the same time, because otherwise just push, you can just push the plane into infinity.
Yeah, yeah. So this is over all samples from both positive and negative classes.
Okay.
Was that the question?
No, but
Okay, let me see if.
Because what I wanted to say, and maybe that's that what you care about is the distance between the closest points from the two classes.
Right.
So whatever.
Also this guy, yeah.
Yeah, so you have to, this is the relative distance that you care about. You can take, because that's what that says, yeah.
Right. So this says we're going to find the closest ones, either from the negative classes or from the positive class, and we want to maximize the distance to the nearest ones. And of course, you don't only push away from the negative ones, because then your margin here is going to be too small.
Yeah, but where are the classes separated there in the equation? It's really silly, but how? It seems
What?
there that you are either
Yeah.
over one
Okay.
class over everything.
No. So what happens? I think I understand what's confusing. What's confusing is what happens if I move this line all the way here? Well, what is the margin now? Well, the margin that's a really bad margin, right? We wanted to maximize this, but now, right, we wanted to push it more than that, but now it's going to be, as I move let's do the following. I'm sorry, I'm moving all this. Okay. Imagine in your mind that this line tries to move. We want to push it away from this. Instead, imagine that this is fixed and I'm just moving all the data, okay? So these blue points, these positive points, they become closer and closer to the separating hyperplane. This is like the margin is getting smaller and smaller. Now it went to the other side. Now the margin is negative. It's really small. It's negative. If the plus is here, that's not a large margin. That's a very small. It's a negative margin. It's not only small. It's a negative. It's a really bad margin. So I think what I was confusing you a bit when I said that the margin is the distance. It's not exactly the distance. It's the signed distance. You care about what side of the hyperplane it is. And you want to maximize, you want to push it away from the right side. Otherwise, it's going to be negative, and that's even worse. Does that help? Great. Yes?
How do you choose, or should you choose the number of points that support the vector, the closest point?
This should come out of the optimization. We don't choose that.
No, but you said you're not going to calculate for the distance, the margin from all points?
Yeah, you do. This is okay, this is all I in 1 over n, all the data.
So you do calculate the distance from all the points.
In order to know the smallest one.
I mean, there are many ways to do that. You ask numerically. We're gonna show how we optimize this. But you're right. One way to do this is to compute this for every point, and then make small, let's say, gradient descent in W or something. That could be one way to do that. More questions? I think the question there was about the fact that the margin is signed. It has a sign. Margin could be negative. The margin could be negative, which means that is on the wrong side of the hyperplane. That's actually important. So thank you for pointing this out. Okay. So we want to solve this. Let me massage this optimization problem and rewrite it. We're going to follow a few steps. I'm going to rewrite it in a way that's easier to optimize. Okay. Good. So now comes this is the hardest part. You remember I told you we divide by the norm of W because we want it to be not sensitive to the scale. Now what this means is, imagine that I have a solution W. Let's say there's some, for any solution W star, if I just multiply it by a scalar, that's also a solution. Right? If there's something that minimizes this, maximizes this, then multiplying it by scalar just gives you the same value, so it's also maximized that. So for every W, we actually have a family of solutions. And so let's not do that. Let's choose one member of this family. Okay? So to choose one member of the family, what you can do is you can decide to fix the denominator, or you can decide to fix the numerator. So it's a bit more intuitive to fix the denominator, let's say norm of 1, but we're not going to do that. We're going to do the non-intuitive one, which is fix the numerator. That's the part that's always most confusing. Okay? So just note, when you want to maximize a ratio, you can either maximize the numerator or make, right? You can make the numerator larger or make the denominator smaller, right? So we're gonna constrain the numerator. So the first, actually there's one step before, there's one step before that, just a very simple step. First, note that I can put the minimum over I at the numerator, right? Because all of them have the same norm. So I can just put it, I can rewrite it like this. That's fine, right? Now, so that was like step 1. Step 2 is, as I said, for every W, which is a solution, CW is also a solution. So we're going to select, let me see how I write that. So I'm going to tell you there is a solution, there is a C for which the numerator obeys. Then there is a C for which the numerator obeys yi. For which the numerator obeys that yiw transpose xi is larger or equal to 1. Because we can just play with all these C's, and I want to choose C that such that this is obeyed. And this will allow me to choose one member of the family. You could have asked, why don't you choose it to be equal to 1? And I'm going to tell you, this is because it's going to make optimization a bit harder. In practice, the solution is going to be achieved for equal 1. But at this point, I'm just going to have a soft constraint larger or equal to 1. So what this gives us, I'm telling you, this is going to be equivalent to the following problem. You maximize W of this such that minimum over I of yiw transpose xi is larger than 1. Let me see if there is something I can clear about that. And I know this is the part that is always the least intuitive and a bit confusing. So you need to spend a few minutes and think about it. Take a time after the talk and see that this step is that you can grasp it. Okay? It takes a bit. You need to think about it. The next few steps are much easier. If you want to maximize over W 1 over norm of W, this is equivalent to minimizing norm of W, right? It's the same, right? Because clearly the solution to this would be the solution to this. The next step, right? So this is 3. The next step is the following. If I'm telling you, there's
Explain the constraint.
this one.
Why are you taking a constraint of 1?
Oh, why 1? This is just an arbitrary number. You just want to set the scale of the problem. I remind you that the reason we divided by the norm is because among all the zoom in, zoom out, we want to select one member of this family. Again, for every W, we only care about the orientation in space. We don't care about how much zoom in or zoom out we have because right, the line looks the same if you look at it zoom in or zoom out. So by adding this constraint, you kind of set the scale of the problem.
But is this a hyperparameter of your model?
No. This is just, it's not a hyperparameter. You can just select one scale. You could alternatively said, I'm going to limit my optimization to W's whose norm is 1. You could have done that. And this also select one member of the family of W's.
You're trying but to prove some unrelevant solutions with this constraint?
Well, there are equivalent solutions. So what I'm saying is that when you solve this, solutions fall into families. For every solution W, all the multiplications of W, right? All scalar times W, they're also a solution. So then you have like a full set of solutions, and we want to choose one. And there are several ways to choose one. You could have decided, I'm going to fix the norm and limit the denominator. Instead, we constrain the numerator. And to do that, we just say, OK, let's constrain the numerator to be larger than. And 1 is just arbitrary, right? It should be any scalar. I know it's a bit confusing. You need to read it again and see that it works. So this step was simpler. Now the next step is the following. Look, I'm looking at solutions that obey that the minimum over this is larger than 1. Now this is equivalent to asking that all samples obey that are larger than 1. OK? So what I'm saying is this is also equivalent to the following problem. Such that yi w transpose xi larger than 1 for all I equals 1 to n. Let's see why this is true. If the minimum is larger than 1, then everyone is larger than 1, right? On the other hand, if all of them are larger than 1, then the minimum is larger than 1, right? So these two are equivalent. But note that here, in the constraint, you have this minimum. And you have one constraint with a minimum function, a minimum operator. And here you have n different constraints. So we moved from an optimization problem where you optimize under one constraint to an optimization problem where you optimize this under many linear constraints. And the number of constraints is the number of your data points. OK, and there's one final step. We're looking at to find a minimum of this function. And it is allowed, if you're looking for a minimum, you can take the square, because the square maintains where the minimum is obtained. Right? If you have a function, you take a minimum, you take a square, the minimum is going to be kept at the same point. So you can finally rewrite this as the following. You know what? Let me write it here, back here. So we got from here to an equivalent formulation that looks like this. We are trying to minimize the squared norm of w under n constraints. yi w transpose I xi is larger than 1. And what I'm telling you, and you should sleep on it, is that this optimization problem is equivalent to this optimization problem in the sense that the optimum of this is the optimum of this, right? They have the same optimum. They don't have the same value of the optimum, but they will give the same optimal w, the same value of the separating hyperplane. Now, OK, we did all this work. Is this much easier? Well, yes, because this is actually a quadratic function, right? The norm of w is just, right, w1 squared plus, right? This is just a square function with linear constraints. And it turns out that this is a class of optimization problems called quadratic programming. And there are efficient algorithms to solve it. Let me give you intuitively why is it easier to solve. Basically, you have a quadratic function, right? Imagine this like a bowl, right? Like a high dimensional parabola. Let me draw that so we have some intuition. So you have kind of a parabola here, right? It's like a big bowl. And you're looking for the minimum. But you're not allowed to find just the minimum of w because you have constraints. But the constraints are linear. If you look at the space of w's, right, this is norm of w. And of course, we're talking high-dimensional parabola, right? But I can only draw two-dimensional. Let's say this is the space of w. every sample gives you a linear constraint. So you have an xi, yi, it constrains you that, right, it gives you a constraint over w, so you're only allowed to be, let's say, on this side. And then there's another sample, you're only allowed to be on this side. Sorry, right? You're only allowed to be here. And then there's another one that you're only allowed to be here. So you're looking for the minimum of this, but your search space has all these separating half spaces that allow you to be only on one side, not the other side. And of course, there is a solution because we know that the data is linearly separable. Yes?
Where do we see the effect of the xi and the yi in what you draw?
Right. So each sample basically give you here a linear constraint. So yixi, here I remind you it's a bit confusing, right? Because here the unknown parameters are w. So what you get here, xi, yi are the numbers, and w is your unknown parameters. And what does obey this linear constraint? This defines a half space that obeys this, right? Yes.
If we were to choose another form, let's say, to minimize, just choose like the exponent minus, which also uses all the constraints, but is analytically solvable. Instead of minus for all minimum for all i's.
Yeah.
Exponent minus.
You could do that.
Like that.
You could do that. Then you'll get something slightly different, but you could do that. It's true. The difference would be, in this formulation, you only care about the closest points, and you really give no weight or no attention to farther points. Of course, you need to find them, the closest ones.
In your formulation, you consider all the points afterwards.
Well, during optimization, you consider all of them, but at the end, you're going to find w. What's going to decide the w for you are just the closest point. Because let me say in a different way, you're also going to have constraint here and constraint here. They just don't really affect your actual solution.
The same with the exponent. If the argument in the exponent is largely negative, you will not.
Well, because it's never really zero. It would push. Yeah, it's going to be a different solution. Yeah.
Like after you segment the hyperspace into this little small section that corresponds to all those constraints, can you be absolutely certain that this hyperparabola is going to go there?
There's going to be a solution. Yeah. Are we guaranteed there's going to be a solution? Well, yes, because we assumed that the data is linearly separable. So there is a w that obeys all these constraints. Here's one thing that could help us. And again, this goes back to this numerator denominator. You could say, I'm going to fix the scale of w, and then I want to make the margin as large as possible. In a way, what we do here is different. We say we're going to zoom in or zoom out until the margin is a distance of 1. And among all of them, all of the hyperplanes where the margin is 1, we're going to look for the separating hyperplane whose norm is the smallest. Let me say that again. What I'm saying is, because we were, in general, you have this invariance of the scale. You can zoom in or zoom out. They all look the same to you, right? When you look at w, w looks the same to you if you look close or far. Can you imagine this? Does that help? Okay. You do this. So there are two ways to think about it. One says, I'm gonna say a fixed zoom. I'm not allowed to rescale. I'm gonna say a fixed norm of W, and then I'm gonna find a W where the margin is largest. This is the geometric intuition. What we did here is, through all this optimization, we found something that is equivalent, but it's a bit more confusing. Basically, we're saying, okay, for every W, zoom in or zoom out until the margin is 1 centimeter, just 1. And among all of them, find the W whose norm is smallest. And the point is that these two problems are equivalent. So the optimization problem here, what's going to happen in practice is that we're going to find the smallest norm. And because we're going to find the smallest norm, this constraint is going to be equal 1, not larger equal. Because if it was larger, then you can make W smaller a bit. And then this would go to 1, and the norm would be smaller, right? So in practice, the solution is going to be right and at the edge of these constraints. It's not going to be here, because then you can make W smaller. What else did I want to say? Okay. So let me also point out that there are efficient algorithms to do quadratic programming. I think this is actually in most of the optimization, libraries or something. There is a library for efficient quadratic programming. In practice, for SVM, there are specific algorithms because you had the right intuition that actually computing it, all the margins for all the data again and again, this is not efficient. So there are more efficient algorithms to do that for SVM, but in general, you can solve that very efficiently. I want to highlight the geometric intuition about what this optimization is trying to do. Usually in learning, there's a lot of math, but I think this is one case where there's a lot of geometric intuition, and I think it's interesting. Oh, there's echo. Okay, maybe if I stand here. So in this optimization problem, look, what we're trying to do is minimize the norm of W. Think about it as if what we're trying to do is to zoom out. We try to, go far, right? To kind of zoom out. You take your phone and you do this, right? You zoom out. You make everything smaller, which means the scale is going to be smaller, right? The norm of W is going to be smaller. Now, when you make everything smaller, then the margins, at some point, the margin is going to be lower than 1. And what we're saying is that you're trying to zoom out, but you're going to stop once the margin reaches 1. You're allowed to zoom out to everything that is larger or equal to 1. You can zoom in so the margins are large, but you want to zoom out, right? You want to minimize the norm of W. Minimizing the norm of W is equivalent to changing the scale such that everything becomes smaller and smaller. And at some point, the margins become small, and they reach 1. Now, at the same time that you zoom out, you're also allowed to move W, right? So you do two things. You zoom out, and at the same time, you find a W, which is best, and you stop when you zoom out the maximum and at most that you can, and then all the margins are 1. Does that make sense? So you actually do two things. You search for that W that at the same time is the smallest, which means you zoom out at most, but you are not allowed to make it too small because then the points become too close to the hyperplane. So does that make sense?
So you're always going to have a distance of 1 because you're just changing the scale. You choose 5 and then just changing the zoom to 5.
Right. So yeah, you can always have this. I mean, if you're allowed to zoom in, it's easy to make the margins large. But what you're trying to do is to zoom out, make the scale of the space smaller and smaller, but you stop when you reach a scale of 1. And this is exactly what this does. It tells you minimize the norm of W, but notice, you're allowed to do two things. You're both allowed to zoom out, but you also can move, right? the hyperplane. And just back to this drawing. Here, this is a space of all w's. You do two things. You want to make w smaller, but you also can, for every norm of w, you can also, you have a lot of possible w with the same norm, and you look for the one that gives you the largest margin. Yes?
When we defined one was like there was a specific reason for one. Or
oh, because it just yeah, it's just arbitrary. You could have
but if we
pi.
We do whichever number that we do, we will get to the same solution.
Yeah. Yeah, this is just arbitrary scale. You need to know. Okay. So I want you to notice one more thing. You remember we talked about the Hinge laws. And in the Hinge laws, our criteria, I mean, when you get penalized with the Hinge laws, you get penalized. Okay, I'll drop it a bit. Thanks. Is this better? No, my throat is dying. So I remind you, you remember an hour ago. There it is. Oh, the Hinge laws. There it is. I'm not used to these fancy boards. That's very nice. So in the Hinge laws, thank you. When we were penalized if yi w transpose xi was smaller than 0. What about here? We are not allowing, now it's not enough to be larger than 0 to be okay. You need to be larger than 1, right? So in a way, you care about that part, right? You're penalized. In this case, it's not penalizing. We ask you, you must obey, right? You must be larger than 1, not just larger than 0. So this was, so let me switch. This was for data that was linearly separable. And now let's talk about data that is not linearly separable. There are two very different kinds, and we're going to have very different solutions for different types of nonlinearity, okay? Two types of nonlinearity that you mentioned both. One of them is the case where the data is, right? We had this example of pluses and then minuses around. There is some inherent nonlinearity here. Let's wait with this just a second. And there was a question earlier about what happens if you have outliers. What happens if you have a minus here, right? That's bad, but we want to handle that, right? So we have these guys. Also, I think there was, who was it? Was it you that mentioned what happens if there's a minus here or here, right? Maybe it's not that bad, right? Even on the right side, but within the margin. Perhaps we don't want to. Perhaps we don't want to move all the hyperplane just because of one lousy point, right? So this is better for data like label noise, right? If some of your label data has incorrect labels, you don't want to, right? You don't want to completely destroy your algorithm. What you want to do is exceptions, right? It's very common. Let's allow some exceptions. But of course, you don't want to allow all samples to get exceptions, so you're going to pay for exceptions. And the idea is that you're going to pay for exceptions depending on how bad the exception is. So we're going to pay a price. Imagine we have this bad, how do you say, דוגמה סוררת? I'm not sure what's that? Oh, rock. That's right. Rebellious. So we have this rebellious ROG sample here, and we need to drag it back to where it belongs, right? This is a minus. Hey, you should be on that side. So we're going to measure how far we need to drag that. Really imagine someone just pushing this sample all the way here, and it should be all the way until there, right? You want to drag it all the way here. So what I'm saying is that I'm going to allow penalties. I'm going to allow, in addition to minimizing W, I also allow you to have these exceptions, and you're going to pay per sample how much does it kind of the distance that you need to drag it all the way to the right side. So to do that, we're going to define the price we're going to pay per sample. So we're going to have additional variables. So we're going to define, they call it slack variables. Psi I. This is my favorite Greek letter because you just brrr, right? No one knows how it should look. Squiggly, exactly. Squiggly Greek. So we're going to have, for every sample, we have this slack variable. And we now going to have a new optimization problem where we optimize over several things. So as usual, we're going to minimize over W, but now we're also going to minimize over all the slack variables. All the slack variables, they're going to be 0 or more, because we only pay, we cannot gain. We only pay price for dragging these samples. And as before, we have yi w transpose xi. Now, in a way, we say, remember, we wanted it to be larger than 1. But now we say, you know what? It's like a deal. Only for you, just today. Only for you. We give you some slack. We allow you, we're going to help you to be larger than 1. We're going to add that term, that positive term. But of course, this is going to cost you. So at the objective, we're going to pay a price that is the sum of all the exceptions, all the slacks. So this is the new optimization problem. Yes, thank you. And let's, so this is, let me just describe this again. These psi i's, they are these slack variables. The intuition is that this is how much you need to drag that so it is on the right side. And notice that if you have a sample that is already on the right side, then what value of slack of psi I should we give it? 0, right? Because why would it give it 0? Because otherwise we pay C dollars for it. And we don't need it to obey this constraint. On the other hand, let's say an example. What happens if you have a sample just here, right? On this line. How much do we need to drag it to be on the right side of the margin? 1, right? Yeah, this is always 1, right? The margin is always 1. So we're going to, right, for that sample, we had yiw transpose xi equals 0. So if we're going to set psi I equals 1, it's going to be larger than 1. And we're going to pay $1 there. OK? So the optimization problem now is over how many variables? That's a tricky question. How many variables in the optimization problem? 2n? No. No, 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 no. No, no, no. No, no, no. So, OK, how many xi's? N. How many w's? The dimension of the data. It's not the number of samples. W, well, I think I noted that D. It's not n, it's right. So n is the number of samples, D is the dimension of the data. So it's like n plus D. So, but notice, this might be optimization over a lot of variables, right? A lot of variables. Because now you have another variable per sample. What about how many constraints do we have now? Now it's 2n, right? I didn't write this. This is for every I 1 to n, and also we have a slack variable, and they're all 0. And they're all positive. OK. There's also usually, for some reason, it's not written exactly this way. It's written in the following way. You ask it to be larger than 1 minus psi I. For some reason. I don't know. That's OK. Now, I want to ask you, what happens? I mean, how much should psi be? Imagine I have some sample. What value of psi I? Let's for fixed w. What should psi I be? So look, if w transpose xi is larger than 1, then OK, psi I should be. If it is larger than 1, then what should psi I be? 0. If it is right, otherwise, what should you make psi I? So that is, yeah. So this is going to be 1 minus y w transpose xi. Right? Is that true? Let's see if we put that here. Yeah, that's what you get. Right? Now notice that psi is how much you pay, right? So in a way, this is your loss, right? Our loss currently has 2 components. One is the norm of w, and we're going to talk about this in a bit. I'm sure you talk about regularization. We're going to talk about that in a bit. And the other is this loss about misclassification. So note, I think this form, it should look a bit, familiar to you. Does it remind you anything? Yeah, it should have been there. I'll remind you how the Hinge loss looks like. The Hinge loss, let's write it here. So the Hinge loss looked like this, right? The Hinge loss was 0 if yi w transpose xi larger than 0. Otherwise, it was minus yi w transpose xi. Right? That was the Hinge loss. What we have now is a Hinge loss with the only difference. Can you see the difference? The only difference is this 1 here. I think it's fun that it comes out, all these Hinge losses. Okay? But so what happens here is a new loss that is like a Hinge loss with a margin. Basically, it looks like a Hinge loss where you just shifted it a bit. So again, if you're inside the safe zone, right? If you're smaller than 1, you still pay a price. So I think that's interesting, right? We started from a really geometric criteria of pushing making the margin large, and we actually discovered that what the SVM problem is trying to do is to minimize kind of a Hinge loss with a margin. This is this part, and together with another component that it looks at to minimize the norm of W. So you can think about what, and I told you this approach called support vector machine. It's called support vector because, as I told you, right, it's kind of silly, right? The samples that are closest to the separating hyperplane, they kind of hold it. Have you ever done Yetzirah? I don't know if you do carpentry and you have this plank, right, of keresh, and you want to hold it into, right, you have something that holds it, so you have like support. It's called support vectors because, I mean, everything is vector, and machine because this is a machine learning. It's a weird name. Not the best. I mean, deep learning is a neural network. These are much more catchy names. So, in a way, SVM inherently looks at the Hinge loss with a margin. Now I want to talk about the fact that in our objective function there are these two terms. And I imagine that so far you often saw that objectives have these two terms. One of them tries to push for accuracy, and the other one tries to push for smaller or simpler models. And there is a large theory behind SVM. Perhaps we're going to have time to talk about it next week, that shows that as you regularize, as you minimize, let's say, the norm of W, you can have better guarantees for generalization. I remind you, we started from some intuition that if you keep large margins, it would generalize better, but you can actually prove that. So I think in many cases, you're going to see objective functions that have an accuracy term and a regularizer. Right? Did you talk about this, regularization? Yeah, I'm sure. You did like polynomial regression or logistic regression. You probably had, you talked about ridge regression? Yeah, so you have this term there. But I think one thing that's really nice here, you see that this term, it kind of came very intuitively, right? We didn't start with like plugging in this regularizer. It came out from the notion that we want to maximize the margin. And indeed, SVM is one technique in a family of problems that's called max margin techniques. So perhaps with different approaches, someone told you, oh, yeah, let's just minimize also the norm of W, the square norm of W. But now there is some strong intuition of why it appears there. This all came from this zoom out thing. OK. So let's do, I think we have about 15 minutes, right? Yeah, 10 to 15 minutes. Let me try to do the following. So the next step, we talked about nonlinearity of how to handle these rogue, rebellious samples. We also want to handle real nonlinearities, like this example, where you basically want to have a square or something. We want to introduce nonlinearity into the problem. So this is going to be tricky. So we're going to do a few minutes of some theory of optimization. It's going to be kind of a sidetrack. And then we're going to continue next week with using these techniques to introduce nonlinearity. OK, so hold tight. This is the hardest math part of the talk. OK. So I'm going to tell you, now I'm going to need my notes. So I'm going to tell you a bit of theory about constraint optimization. You've seen we have constraint optimization. This is natural here, right? We try to often minimize the norm under some constraints. So let me tell you a bit about more general theory of constraint optimization. So in the general form of constraint optimization, you have some function f of x and f0. And here, we kind of leave aside the notation of machine learning where x are actually numbers and w is zero parameters. We go back to like analysis function chedva, where x are your variables and you have some f of x. Okay, so here x are your variables, not like w in machine learning. And the idea is that you want to find the minimum of x, but you also have some constraints. Let's say you have fi of x smaller than 0, and you can have m such constraints. Okay? Questions? Okay. So so how do you solve this? The main trick, the main idea is to take such constraint. Maybe let me step back. When you want to optimize a function without constraints, then you learn that in kindergarten, right? You compute the derivative and you find equate to 0, and you find a minimum. That you know well. But hey, what happens when you have these constraints? You take the derivative. What do you do if it doesn't obey the constraint? Okay. So the trick here, the idea is to somehow replace the constraints with penalties and put these penalties into your objective function. Okay. So here's the idea is that you define the following function. Sorry. And this lambda is going to be a vector. And we're going to define this Lagrangian where actually, one more note I forgot to say about this. When you do constraint optimization, you could have minimization problems or maximization problems, or perhaps your constraints are going to be larger than scalar or smaller than scalar, right? There are all these variants. And it's useful to have one canonical. So this is kind of the canonical problem, right? You have minimization, and the constraints are smaller, equal than 0. And if you have maximization, then you just need to fix, you multiply by 0, by -1, -1. So the idea is that you define this Lagrangian function, and these lambdas, they are called Lagrange coefficients, Cofflet-Lagrange. How many of you have done this in the past? Oh, good, good. So maybe that would be easier for you. And they're also called dual variables. And now we also define the dual function, which is a function over these dual variables. And the dual function is defined in the following way. It's the minimum of the Lagrangian over x. So for every value of lambda, you minimize over x, and that's the value you assign to g of lambda. You cannot do that in practice, right? But conceptually. So this means you have minimum over x of f0 of x plus all these Lagrange multipliers. Okay. Fi's are other functions that define your constraints. For example, in the, here, you can see this is just an instance, an example of that case. It's a bit confusing because here the w's are your variables, but you see here f is the quadratic function over the vector x, right? This is the quadratic, and here you have again n constraints. Each one of them, let's say here, fi of w, right? Because w is the variable here, is right. It should be smaller than 0, so we need to move this to this side. So it's like 1 minus psi I minus yi w transpose xi. So that will be fi. So these are the constraints, and in general case, you can have any form. So I just want to tell you about the following property. I want to be careful here. This is why I'm looking at this. The point is the following. There is an interesting relation between this function, which is called the dual function, and f. And it turns out that is guaranteed that g of lambda is going to be smaller than f of x. So it always happens that you have f of x, f0 of x, and you have g of lambda. The g of lambda is a kind of a lower bound on f. So let's just show that. I think I have the proof here. Do I have it? Yeah. Oops. So the claim is that if p star is the value, the minimal value, right? Minimum. Sorry. Right? If x star is the minimizer of f0, and p is its value. So if, right, you have here p star, right, this is x star p star. X is this is the best x, and the output of f0 is p star, right? This is the minimum of the function. The claim is that g of lambda is smaller than p star. Now, this is useful, right? Because sometimes you have functions it's hard to optimize, but well, you have a lower bound. Sometimes the lower bound is very useful. Well, perhaps you cannot find exactly the minimum, but you get a lower bound. And this full function is a lower bound. So let's just prove that. Sorry. I want to be careful here. So here's the proof. Let's look at any x. And I remind you, this equals, by definition, it's this thing. Lambda I fi of x bar. And x bar is just any x. Now, remember that, x bar is any feasible x. That is an x that obeys the constraints. Okay? So if it obeys the constraints, what can you tell about fi of x? It's negative. And lambda I are positive. So all this is negative. So this is smaller or equal than this, just because it's a feasible function, feasible x bar, right? Feasible means it obeys the constraints. So now g of lambda is minimization over x of x lambda by definition. So this is smaller than L x bar lambda. Smaller or equal. And this is because, well, here you try to minimize the Lagrangian. So the minimizer of the Lagrangian, of course, is equal or smaller than just this arbitrary x bar that you've chosen. Okay? Because That's the minimum. And of course, we saw this is smaller than this. Now, what happens is, this is true for any, this holds for any x bar which is feasible, especially for x star. So if you just plug in x star here, you get that g of lambda is also smaller than x star. So g of lambda smaller equal to f0 of x star, which is p star. So what I proved to you is that this dual function gives us a lower bound on the optimization problem that we are interested in. Now, lower bounds can be useful, but the gap might be very large. So in general, we would love cases where this gap is small. And I can tell you, perhaps we're going to prove it next time, that there are special cases where this gap is 0, which means the maximum of g lambda. Oh, let me just stress the thing. G of lambda gives you a lower bound, and the best lower bound is the maximum of g lambda, right? This gives you the best lower bound. So in a way, to find the lower bound, to find the best lower bound, you want to maximize g of lambda. So you have these two dual optimization problems. You want to minimize f of x, and to get a good lower bound, you can maximize g of lambda. I mean, what do you gain? Why would you do that? Well, it turns out that g of lambda often is easier to optimize because it is guaranteed to be convex. So there are techniques that are easier to apply to g of lambda, and then you get a good lower bound. It turns out that if your original f obeys some constraints, some properties, for example, if it is convex and has other properties, then the gap actually becomes 0. So if your original f is a convex function, then your g, the maximum of g, is going to be the same value as the minimum of f. And what we're going to do next time is we're going to see that how we take the solutions for the SVM. Here's the plan for next week, okay? We're going to have the optimization problem we had for SVM. This was defined in terms of f. We're going to transform it to the dual function, and we're going to try to maximize it. And in our case, f is convex, so the solution to the maximization problem of the dual function is going to give us the best solution, exactly the solution of the minimizer of the f function. Now, all that is a lot of work, but the reason to do that is not going to be because it's easier to find the solution. I told you it's easy to find the solution, but this would allow us to write the solutions in a new way where we can introduce nonlinearities. So that's the game plan. Take the optimization problem, write it as a dual problem, write the maximization, then introduce nonlinearity. I think that's it for today. Thank you so much.